All right, so now we're going to switch gears from the alkanes and we're going to take a look at a couple other families of hydrocarbons. And these are going to sound similar to alkanes, but they're fundamentally different. And these are going to be the alkenes. So these are going to have a E-N-E ending compared to the alkanes. And then we have our alkynes with a Y-N-E ending. And I'm just going to put alkanes here as a reference. All right, so the differences between the alkenes and the alkynes compared to the alkanes is that we're going to see in these two families, we're going to see different types of bonding. And specifically, we're going to see multiple bonds present. And specifically what I mean by that is, for the alkenes, for instance, we're going to see carbon-carbon double bonds. And then for the alkynes, we're going to see carbon-carbon triple bonds present. Right, and when we have molecules or compounds that have double and triple carbon bonds present, we're going to call these unsaturated hydrocarbons. Right, and they're called unsaturated, right, because they don't have the maximum amount or the maximum number of hydrogen atoms connected to the carbons. Right, if you remember when we talked about the alkanes that were saturated, right, they were called saturated because these contained the maximum number of hydrogens. So they were saturated with hydrogens, in other words, in the compound. So when you have these double and triple bonds, that means you have an extra bond between the carbons, or an extra two bonds between the carbons that could normally be taken up by a bond to hydrogen, right? So we say that they're unsaturated. Now, what that means is that we can actually convert these alkenes and alkynes into the corresponding alkanes by adding hydrogens to them. Right, and that is actually one of the most common, actually the most common reaction that your alkenes and alkynes are going to undergo. They're called addition reactions. And if we add hydrogens to them, well, we're just saturating them with as many hydrogens as we possibly can. All right, so let's take a look at each of these families here in turn. So your alkenes are going to contain one or more of these carbon-carbon double bonds. And when you draw your alkenes, there's a couple ways that we can represent them, right? So we've seen the ball and stick model that looks like this, and then you have your expanded structural formula that looks like that. All right, and what we can do is we can condense that even further, and we can say we have a carbon-carbon double bond, and then we have an H or two H's connected to each of those on either side, right? So we have a CH2 connected by a double bond to another CH2 on the other side, right? So you'll see this being used in your textbook as well. The other way now we can represent the alkenes is by using the line angle formula, which we'll see here in a second. So a couple of things to note here about the environment around that carbon-carbon double bond. So you'll notice here, if you were to focus on this carbon, you'll notice that it has 3 electron groups around it, right? 2 single bonds and a double bond. And if you remember from your Lewis structure chapter, when you have a central atom with 3 electron groups around it, they adopt a characteristic shape called a trigonal planar shape. Right, and that's actually the shape here around that carbon-carbon double bond, and the bond angle is 120 degrees, right, all the way around between each of these 3 bonds. And that is compared to the tetrahedral shape, right, that we have in, or when carbon has 4 single bonds. So the molecule is going to look very, very different, right? Trigonal planar is flat, tetrahedral is not. So having that double bond imparts some significant structural differences between your alkenes and the alkanes. The simplest alkene that we have, well, the smallest alkene that we have is called ethene, right? So eth here meaning 2 carbons. And the ENE now, right, just as the ANA told you something was an alkane, ENE tells you that it's an alkene, which means there's a double bond present, a carbon-carbon double bond. And ethene specifically, it goes by a common name called ethylene, right, that's the common name for it, is implicated in the molecule that actually is responsible for the ripening of fruits, right? So bananas, for instance, turn yellow as they are exposed to ethene. So we can say that your alkenes, we'll look at the naming here in a second, alkenes will all end in ENE, just like your alkanes all ended in ANE. Alkynes, on the other hand, are characterized by having a carbon-carbon triple bond. All right, so here we have the simplest alkyne. Right, so if you have a carbon-to-carbon triple bond, that means the smallest alkyne is going to have 2 carbons in it. So we're going to have a C, a triple bond to another C. Carbon likes to form 4 bonds. So the 4th bond here to each of these carbons is going to be to an H. All right, and sometimes this is represented in a condensed way like that. If you were to build a model for this molecule, so 2 carbons would be, the prefix for 2 is eth, and then an alkyne would have that YNE ending, right? So ethyne means 2 carbons, YNE means there's a triple bond between both of those carbons. So here, if we look at our carbon in either of these, there's 2 electron groups around it, right? When you have those 2 electron groups, the shape that it adopts is linear. And that's exactly what we see here. This molecule around the carbon-carbon triple bond, this shape, or that bond angle there is 180 degrees. So this here is going to be a linear molecule. All right, so your alkynes, the names will end in YNE. All right, so let's take a look now, a little closer look at how we name the alkenes and the alkynes. And we're going to see some similarities between the naming system for the alkanes as compared to the alkenes and the alkynes. There's one thing, though, that we need to pay special attention to when it comes to naming the alkenes and the alkynes, and that is the presence of the double or the triple bond is going to take precedence when it comes to establishing the longest carbon chain, and then when it comes to the numbering as well. All right, so we're going to follow the systematic way, which is the Iupac naming system. And then this rule here is going to apply to both alkenes and alkynes. So just like with the alkanes, we want to get the longest continuous carbon chain. Okay, and we saw that for the alkanes, but the extra thing that we need to address now is that longest continuous carbon chain must contain both carbons of the double or the triple bond. All right, so that limits in terms of, or it limits how you're going to establish your longest carbon chain. It has to contain both carbons of the double or the triple bond. The presence of the double or triple bond also establishes your numbering system. So we're going to number the chain to give the lowest number possible for the carbon that starts the double or the triple bond. And then, as we saw, we'll use the ending or the suffix ene for alkenes, or yne for alkynes. All right, so there are some similarities in how we're going to address the naming that are similar to the alkanes. The only difference now is the presence of the double or triple bond are going to limit where we establish the longest chain to be, and also the numbering system. If there are any substituent groups or branches hanging off of that longest chain, then we're going to name and number them appropriately as well. All right, so let's take a look at some examples of these, just to sort of illustrate these points. All right, so here we have, we'll take a look at A first. All right, so a couple of things to establish. The first is you will notice that there is a double bond right here. All right, two lines between two carbons would mean a double bond. Right, and you notice when we draw it, we still draw it in the zigzag fashion because the shape around that double bond is trigonal planar. Right, so we need to faithfully replicate that in our structure. All right, so double bond present, right? So that means that it's going to be an alkene. So we need to establish the longest continuous carbon chain that contains both carbons of the double bond. So we can start on the left. So this is 1, 2, 3, 4, 5, and we get 5 carbons. We can also go 1, 2, 3, 4, 5 and end on the bottom. We can also start on the right side and we can go 1, 2, 3, 4, 5. So whichever way we slice it, 5 is the longest. All right, so 5 carbons. All right, so 5 would mean that it's pent. There's a double bond in it. So it's an alkene, so it's pentene. Okay, so now we've established the longest carbon chain that contains both carbons of the double bond. Now we have to say where that double bond starts. And we're going to choose a numbering system that gives the lowest number to the start of the double bond. All right, so if we look at either the red or the green numbering system, the carbon that starts the double bond is here, right? And either in the red or the green, right, that's carbon number 2. If we were to use the orange numbering system, when we go from right to left, the carbon that starts the double bond would be here, and that's carbon 3. All right, so 2 is lower than 3, so we're going to choose a numbering system from the left side. And that means that carbon number 2 starts the double bond. So we're going to say 2-pentene. Right? So this here tells us where the double bond starts. Okay. Now, we've established the longest chain is 5-pent. We've established it's an alkene, so ene, pentene, and we've said where that double bond starts. Now you'll notice that there's also a branch hanging off of this thing, and it's on carbon number 4. Right, and this here, if you remember, that's a methyl, a 1-carbon chain, or 1-carbon group, or substituent, and it's on carbon number 4. So we're just going to insert that at the front. 4-methyl -2-pentene. Right, so that tells us exactly what we have in our compound. So it's systematic, and we use the same sequence of events to name it. We established the longest carbon chain, but now we're making sure that both carbons of the double bond are in that longest chain. We're going to number that chain to get the lowest number possible for the carbon that starts the double bond, and then that locks in our numbering system. Right, so once we establish it as 2-pentene, we're saying we're going to number it from the right side, from the left side. So then that methyl group is going to be attached to carbon number 4. Right, so 4-methyl 2-pentene. If we take a look at the one underneath, all right, so here we have, and this looks a little weird or unusual, but that's 3 lines, and that's a triple bond. Right, and the reason why it's drawn like this is, remember, around a triple bond, the shape is linear. Right, so everything around it is a straight line. So the important thing to keep in mind here is where the carbons. So there's a carbon that starts this line, right? And there's also a carbon that starts or ends the triple bond, and there's also a carbon that ends the triple bond on that side. There's a carbon here where 2 lines intersect. There's a carbon there, and then there's a carbon where this thing ends. So there's a total of 1, 2, 3, 4, 5, 6 carbons in this. So 6 carbons would mean that it's a hex. Okay, there's a triple bond in it, so it's hexyne. And now we need to number this carbon chain to give the lowest number possible for the carbon that starts the triple bond. All right, so if we start on the left side, this is carbon 1, 2, 3, 4, 5, and 6. So our triple bond would start on carbon 4. If we were to number it from the right side, then this is 1, 2, 3, 4, 5, 6. Here our triple bond starts on carbon 2. So we'd choose a numbering from the right side because the triple bond starts on the lower carbon and it starts on carbon 2. So we would name this 2-hexyne, right? So the 2 here tells us, the 2 that immediately precedes the ending tells us where the triple bond starts, right? Just like in the naming the alkene, we saw that the 2 here told us that the double bond started on carbon 2. Here we're saying the triple bond starts on carbon 2, or triple bond starts. All right, so the key thing that hopefully you're seeing here with the nomenclature and the naming is that it's systematic, right? We're following the Iupac way, the International Union of Pure and Applied Chemistry, that establishes rules for naming these things. Everybody follows those rules so that when we name something, we know exactly what that thing is and what it contains. All right, so what if we had cyclic compounds, right? So if we have we looked at cycloalkenes before. We can also have alkenes that come in rings, which we call cycloalkenes. So these are going to have a double bond within the ring structure. So when we name the ring structure, we need to include the fact that it's got a double bond in the structure. So for example, if we had something like this, so looks like a square, and we had a double bond on one side. All right, so 4 carbons in a ring would be cyclo, that's a ring. There are 4 carbons in a ring, the prefix for 4 is but, and now we have a double bond here, would give us that Ene, right? So a ring structure with 4 carbons with a double bond in it. In this case, we don't need to say where the double bond starts because we can only start at carbon 1 because it's a ring structure, and that would be the only obvious place to start numbering. If we have a ring structure with some substituents or groups hanging off of it, then we would need to name a number where those groups are located. All right, so here we have this structure here underneath. All right, so we either find the longest chain, or in this case, we have the ring structure, and we're gonna name that ring structure. So let's identify it. This is what we're going to be looking at here. So looking at it, looks like a pentagon. All right, so that's 5 carbons in the ring. All right, so that would make it cyclopent. And there's a double bond in it right here, so that would make it an ene, so cyclopentene. And then we have a methyl, a CH3, that's attached to one of the carbons. All right, so when it comes to numbering the ring, right, we said that what takes precedence in the numbering is the double bond, right? And we want to give the lowest number possible to the carbon that starts the double bond. So we have a couple choices here. All right, we can start, if we wanted to, we can start here with carbon 1, and you always number through the double bond. Right, so in other words, I couldn't go 1, 2. Right, I couldn't go to the left. When you number the double bond, you have to number through it. So if I start here at the top as carbon 1, then I have to go this way. This has to be carbon 2. And then that would mean this is carbon 3, 4, and 5. So if I number it starting at the top, I have to go clockwise, which means my methyl group ends up being on carbon 5. And that's one option. The other option is to start here as carbon 1, and then I have to go this way and number through the double bond. So this is 1, that's 2, and then my methyl ends up being on carbon 3, right? That would give the lowest number possible to both the start of the double bond and also now to the substituent group. All right, so now that methyl is attached to carbon 3, we say it's 3-methyl cyclopentene. I don't need to say 1-cyclopentene because it's understood in a ring structure that the double bond is going to be between carbon 1 and 2, right? So let's just specify this. This is for a ring. Or cyclic. That's the only time, or one of the only times where you don't need to explicitly state where the double bond actually is located. All right, let's take a look at a couple other examples over here. So the first one on the left may be a little too easy, I guess, or maybe not, depending on how well you are absorbing this brand new language in chemistry. So we have a ring structure. How many carbons are in it? We have 1, 2, 3, 4, 5, 6. All right, so 6 carbons. That's a hex. It's in a ring, so it's cyclohex. And then we have a double bond right here, right? That would make it an ene. So cyclohexene. I don't need to say 1-cyclohexene because it's understood in a ring that the double bond is going to start on carbon 1. Okay, over on the right side, we have another structure. Here it may look a little complicated, but what you want to try to do is either find the longest chain, or in this case, there's a ring right here. All right, and that's a 5-carbon ring. That would make it cyclopent. There's your double bond, so that would make it a cyclopentene. And then our challenge, if you notice here, is you'll see that there are a couple groups hanging off of that ring, and these are both methyls. Right, there's a methyl here and a methyl. So we have 2 methyls, right? And if you remember, when you have 2 of the same thing, we just put a di in front of it. So it's dimethyl. And we have to say, using our numbers, which carbon are those methyl groups attached to. So let's see how we can number. We're going to start numbering using our double bond as our guide. So we can start numbering here. And if I start that carbon on the top as 1, this has to be carbon 2, right? You have to number through the double bond. So I go 1, 2, 3, 4, 5. So I end up with my methyls, both of them attached to carbon 5. If I go the other direction, so if I start here, and that's carbon 1, 2, 3, 4, 5, right? Then your methyls end up being on carbon 3. 3 is lower than 5. So that's the numbering system that we're going to use. So we have both of the methyls attached to carbon 3. So we're going to say 3, 3, right? You have to say where each of the carbons, each of the methyls are attached, and both of them are attached to carbon 3, so you have to say 3 twice. So that's a 3,3 dimethyl, and then we're just going to stick that in front of our cyclopentene. So we end up then with 3,3 dimethyl cyclopentene. Okay, and as you can probably see, right, when you start naming your organic compounds, and these are relatively small organic compounds, and even though they're so small, the names look like they're huge. So you can imagine, you know, if you were to name a compound that's maybe twice this size or 3 times that size, how long the name can be. And I would encourage you, if you look up, you know, any sort of drug, over-the-counter medication, that is, or prescription drugs, if you look up their, you can just look it up on Wikipedia or Google if you'd like. If you look up the actual chemical name for a lot of those drugs, you'll see that they are like, you know, a whole couple sentences long if you were to name them systematically. Right? We're never ever going to run into that in our class, but I just want to give you an idea that if you were to follow the rules, right? The rules, if you name these organic compounds following the rules, the name should tell you exactly what you have in the compound and where everything is located.